Okay, this is going to be our first video in our second module for this course, and this module is going to be on electric flux and Gauss's law. And so this is going to be chapter 22 of the text mostly. Okay, and so in this chapter we're going to use sort of symmetries and Gauss's law to do more calculations with electric fields. So we're going to try to find the electric field outside of more objects using Gauss's law and certain symmetries of depending on which problem we're looking at, right? We're also going to find later in the chapter that Gauss's law gives us some interesting insights into how electric charge distributes itself in conducting bodies, right? So we'll take a look at that, but that'll be later on in the chapter. Before we even get to Gauss's law, we need to kind of get a good idea of what we mean by electric flux. We need to have that concept well in hand to be able to talk about Gauss's law effectively. So let's get started on electric flux. The textbook breaks up electric flux into sort of two sort of sections in chapter 22.1, or section 22.1 I should say. It does a sort of qualitative look at electric flux. So we're going to talk about that, and then in section 22.2 it moves on to do calculations with electric flux. Okay. So I'm going to do it exactly that way, so I stick to the textbook, so we have a few sources of ways you guys can kind of get this information. Okay, and so let's get started. So far we've been interested in the electric field at a point given some either charge distribution or some collection of point charges or whatever, right? So in the past chapter we looked at, say, the electric field outside of a single point charge, and then we looked at a few point charges, and then we looked at a charged rod and a charged surface and so forth, right? So far we've been given the charge distribution, and then we're asked to find the electric field at some point outside that charge distribution, right? But what if we flip the question on its head? That's kind of what we're going to be doing here. We're going to be given the electric field at a number of points around a charge distribution, and then we want to try to gain some information about what charge distribution has created those electric fields. So more specifically, we're going to be taking some charge distribution or some number of point charges, enclosing it in a closed surface, looking at what the electric field is at every point on that enclosing surface, and then trying to tell something about, or trying to say something meaningful about the electric charge enclosed in our surface. Okay, so there's kind of a couple of topics we need to go over. First off, we need to know what a closed surface is. Okay, so formally a closed surface is any surface that completely encloses a volume, right? So we can think of almost any 3D shape that you can draw will enclose some sort of a volume, and it can be used as a closed surface. We're going to often use things like cubes or boxes, like rectangular prisms, like shapes like these here. So let's say this is our enclosing surface, this rectangular box. We'll use things like spheres. Shapes like that are going to be the easiest for us to work with, because we're going to find that we need to integrate over these shapes oftentimes, and if not integrate over them, we at least have to have some good concept of what their surface area is. Okay, and so that's what's meant by a closed surface. We're going to use that idea a lot in this chapter, so we want to be clear. Also I should mention, as I note here, that any sort of closed surface that completely encloses a volume would be called a closed surface, but we're going to be interested in sort of imaginary closed surfaces. So when we're enclosing some charge in a box or in a sphere or something, we don't really want to be thinking about a sort of physical box covering this thing, right? These are all imaginary surfaces that we're just imagining the electric field at the points where that imaginary box would be, right? So we're not actually physically enclosing anything in any kind of sort of physical surfaces, right? These are all imaginary. Okay, so let's move on to the idea of electric flux. So I think we mentioned this in the first chapter. An electric field itself can't flow. Okay, so there is no flow of an electric field. The electric field is just a vector pointing in a direction at a certain point in space, and it's caused by some sort of collection of charge nearby, right? And so the electric field itself can't flow, but the concept of electric flux gives us a way to talk about the electric field as though it did flow. Okay, and this is going to be useful to us. Okay, so we're going to want to discuss the direction of our electric field vectors on some surface, on our enclosed surfaces, really. And once we talk about things like flow, or the flow of our electric flux, which is really just the sort of direction in which our electric field points at all those places, and then we imagine that it could be something that could flow, and we can talk about things like, is there a net inward or outward electric flux, right? So we're going to want to look at questions like that, because that's going to give us information about the charge enclosed in these closed surfaces. Okay. So the text spends all of section 22.1 sort of talking about this stuff. I'm going to get right into the sort of pictures or diagrams that they supply for us. So I have a number of them here. I have 4 diagrams here and a few more, and this will kind of give us a good feel for what we're looking at when we're talking about electric flux and these electric fields, right? So let's remember. I'm going to start by looking at this first image here, and let's remember, when we're talking about electric flux, we're talking about the direction of the electric field at that surface, and we're imagining that there's something flowing through there, and that's our electric flux, right? So if we think about a single positive charge like we have here in diagram A in this figure, well, let's remember, we know that a single positive charge, if we think about the electric field lines, remember we drew this in the, I believe it was the last section of the previous chapter, the electric field lines for this will look like this, right? So if we draw the electric field lines, they're all pointing away from the positive charge, right? So anywhere on these electric field lines, we could draw our electric field. Let's say we were interested in this point, we would see that there was an electric field pointing in that direction, right? And so if we plant this positive charge in our closed surface, what do we expect to see sort of punching through the surface, right? We have these electric field lines puncturing the surface here, and we can imagine a sort of net outward electric flux, right? So we have our enclosed surface, we can see all the electric field lines, and we have a net outward electric flux, because every surface that we look at has electric field lines emerging from it going outward, right? In picture B here, if we double the enclosed charge, well, what happens? It's the same idea as we had for the electric field lines, right? Like, let's say we had 2 positive charges, or let's say this was just some plus 2q, where this was plus q. Okay, so we've doubled the strength of our positive charge, the magnitude of it. And so how would we signify that with electric field lines? Well, we would just draw more lines, right? So there'd be more lines emerging from here. And it's the same idea for our electric flux. If we double the charge in the box, we double the amount of flux sort of going through the surface, right? We double the amount of lines protruding through the surface. What if instead we had a negative charge? Well, same idea again as our electric field lines. Now they just all point toward the negative charge, right? And so in this case, we have a net inward electric flux. We have a bunch of field lines pointing inward, cutting through the box, going inward, right? And again, if we double the amount of charge in the box, we have double the amount of flux going into the box. Okay, so those are a few ideas here. What if instead we had no charge in the box or anywhere near the box, right? So there's no electric field around the box. Well, obviously there's going to be no electric flux, right? We have no electric field, sort of air quotes, flowing through the box, and so there is no electric flux passing through our closed surface. Let me skip this one just for 1 second, and let's take a look at this one. Let's say we had an infinite charged plane close to the box. Well, there's no charge in the box, right? And the box is set up such that we're only going to have electric field flowing through this, and I shouldn't say electric field flowing, I mean flux flowing through, but we're thinking of the electric field as though it's kind of like flux, right? So we're going to have flux coming in through this back face, right? And then So there's going to be flux coming in from the back face, and then there's going to be flux coming out from the front face here, and nothing's going to be passing through any of these four faces on the side, 1, 2, 3, or 4, right? Because they are directly sort of perpendicular to the flow of this uniform electric field, right? Like if we remember an infinite charged plate, we're going to have a uniform electric field around it, and so all these electric field lines are going to be pointing straight, and so there is a flux only inward through the back plate and outward through the front plate. And if we added this up, the net electric flux through the box is going to end up being 0, because we're going to have some contribution from the back that will be perfectly canceled by the contribution from the front. And again, there is no electric flux. And this is interesting, because what does that kind of end up telling us? Well, this is leading us slowly to Gauss's law, which we haven't talked about yet, obviously, but we will. So in these cases, we have some net outward flux, and this tells us that we have a positive charge in the box. In this case, we have some net inward flux, and this tells us we have some net negative charge in the box. In this case, over here, we had no flux, no net flux, and so there was no charge in the box. And in this case, again, we do have some flux, but we have no net flux when we add it all together, and so again, there is no charge in the box. And that's what this flux is telling us, right? This electric flux tells us that since there is no net flux through our closed surface, there is no charge in the box. Let's take a look back at part B here, or example B. What happens here? Well, here we have a positive and a negative charge, right? And so if we think about, let's think back to our electric field lines again. If we think about our electric field lines, we're going to have electric field lines emerging from positive charges and ending at negative charges, right? So there's going to be a number of electric field lines that look like this, and so forth. I'm not going to draw them all in there, but you can imagine. And then there'll be some that kind of go further, whatever. This is maybe not the best drawing. And then some of them will simply, be too far off to be able to be drawn in here, right? Okay, but if you imagine that you enclose this thing in a box now, it's going to be all kinds of crazy stuff going on here, and so I've drawn my box as a 2D box here, but you can imagine that it's a 3D box. We're just looking at a slice of it here, right? So kind of what's sort of happening? Well, we can see we have a bunch of electric field lines pointing out, a bunch pointing in. So there's going to be flux coming in and going out of this box. This is not a uniform electric field by any means. Here we have a lot of stuff going on. But if we integrated over all these surfaces, if we added up all the electric flux on each of these faces and added the whole thing up, we would find that it would cancel out perfectly and go to 0. So why is that? Well, again, this is because we have no net charge enclosed in the box, and so there will be no net flux through the box. It's going to add up in such a way that everything cancels out, and this is sort of bringing us right to the doorstep of Gauss's law, which we're going to talk about in a little bit. But for now, all that's important to realize is that if we add up all the flux going in and into and out of the box, it's going to add up to 0 here, okay? And so that's kind of the idea. Maybe I'll leave this in for the notes. Okay, and so the last sort of thing they talk about here is an increasingly large surface, right? So if we have the same positive charge, so let's compare A here and C. So if we compare A and C, it looks like we have sort of a higher density of flux coming out of the box here, and that's true. We have more flux per unit area, but we're interested in the net flux coming out of the whole box. So if we add up all of the net flux coming out of this box and we add it up over this box also, then we're going to find that it's really the same amount, because we have less flux per area coming out of this box, but we have more area. So if you integrate over the full area here, you're going to end up with the same net flux in both cases, right? And this is again important because this flux is going to indicate to us what charge we have enclosed in the box. And again, here we just have a single plus Q, and here we also have a plus Q. And so So we really want to be finding the same result, right? And in both cases, we're going to find the same net flux. Okay, so this kind of concludes. Oh well, what happened to this line? In any case, so we have a line there, but so this kind of concludes what they do in section 21.1. We'll now move on to section 22.2, where they talk about calculating electric flux. Okay, and so I'm gonna talk about all the sort of theory building up to the equations that we need to calculate electric flux, and then in the next video I'm going to devote that whole video to just doing examples of calculating electric flux. But the way that we're going to build up to this idea of electric flux and calculating the electric flux is, first we're going to start off by talking about a sort of analogy that's easier to think about, which is the flow of water. So in a sense, we can think about the volume flow rate, or the timed rate of change of the volume going through some sort of a surface in water, like flowing water, in analogy to electric flux. Okay, so let's start off just talking about water. Let's not think about electricity at all right now. And so imagine that we have a flowing river, right? We have a flowing river, and we're interested in how much water is going through this surface here. So we have some wire loop, and we're interested in how much water is passing through this thing over some period of time, right? So this V, this is our volume, and we're interested in the change in volume over the change in time. And clearly this is going to be related to the velocity of the water, right? Like how quickly this water is flowing in this direction, this velocity vector. What's the magnitude of our velocity vector, and the area of this loop that we're interested in looking through, right? So this is going to be the equation that we would use if we wanted the timed rate of change of the volume of water when the water is flowing at a velocity v going through some loop of area A. Okay? So take a second to sort of digest this equation, and now think about what would happen if instead of using this wire loop facing head-on to the water like it is here, right? Like it's oriented in such a way that the most possible water is going to be going through it. Let's say we tilted this thing. Let's say we turned it slightly, as we have in this picture here. We tilt it slightly at an angle phi. And so what happens as we tilt it at this angle phi? Well, less water is going to make it through, right? Like as we keep tilting it, this velocity vector for the water stays in the same direction, but we're tilting it so that the sort of surface area that it's presenting to the direction of flow of the water is getting less and less. And in fact, if we tilted it to 90 degrees, right? If we had our loop, and I'm not going to be able to draw this effectively, but you can kind of imagine that we had, oh no, I lost it again. Okay, hold on. Let me pause this and reopen that. Okay, so I've reopened it here. We're going to have lost kind of the little notes that I've made along the way here earlier, but that's not a big deal. None of it was super crucial. But like I was saying, so you can imagine that if you turn this wire loop so that our angle is actually 90 degrees, well then it's going to be kind of facing in directly the opposite direction or perpendicular to the flow of water, and no water will be going through the loop, right? And so we clearly need to consider this angle phi when we're doing this calculation, and the way to do that is to include it in our expression here. So if we use this expression, and now we think about going through all the angles from phi equals 0 to phi equals 90 degrees, well, we're going to get less and less. Like we'll have the most volume of water going through per unit time when our angle theta is 0 here, right? Or I should say our angle phi is 0. And then as it slowly cranks up to 90 degrees, we're going to get less and less water until we're actually at 90 degrees, and then no water is flowing through, right? And so this is sort of our expression for the volume per unit time going through our loop. But we now want to make a small adjustment to the way that we think about areas. Okay, and this is going to be a useful tool for us going forward throughout the course and in physics, really. We want to adjust our idea of an area instead of just being sort of a scalar area like we normally think about it, to being an area vector, okay? And so if we think about our area as an area vector, what we want to be thinking of here is that our area vector is a vector that points, well, we can see it in this diagram here, that our area vector is a vector that points perpendicular to our surface, so it points normal to our surface, right? And I'm not sure if people will already be sort of familiar with the concept of a normal, a vector normal to a surface, right? But you can imagine that if you have some sort of a surface, let's say this is just a cross section of a surface, which would really be like have some depth to it, then our normal vector points perpendicular, right? So this would be a normal unit vector, right? And so what we want to be thinking about here is that our area vector is really a vector which points normal to the surface and has a magnitude equal to the area, right? So A, our vector A, is going to really be magnitude A, like the area of that surface, pointing in a direction normal to the surface, okay? And maybe actually this is a useful way to kind of think about it and keep that idea in your head, okay? And so armed with this idea of an area vector, we can rewrite this equation that we have up here, right? This equation 2 we have up here in terms of dot products, right? And so if we rewrite it in these terms, then our timed rate of change of the volume flowing through our wire loop, or whatever we want to call this thing that we have over here, this yellow object, is then going to end up being our velocity vector dotted into our area vector, right? And as A turns away from V, we're going to get less and less, and obviously the dot product, when they are 90 degrees apart, is going to be 0, just like we want. And so this is a very useful sort of way to think about water flowing through this loop, okay? And so if we take this idea, well, if we take all these ideas, if we take this idea of this dV dt, which is a timed rate of change of the volume flowing through, this is really like a flux of water going through the loop. So if we translate this idea of water going through a loop to our idea of electric flux, and then we keep this idea of an area vector, but we just change our velocity vector to our electric field vector, we end up being able to generate an expression for our electric flux. And that's exactly what we're doing here in this next section, okay? So we take our volume flow rate, our dV dt, we replace it with this symbol. So this symbol here is just a capital Greek letter phi, and we give it the subscript E to remind us that we're talking about electric flux. So what are we saying here? We're saying that the electric flux, that's that symbol, is equal to our electric field dotted into our area vector for that surface, okay? And this equation is boxed. This is definitely an equation you want to have at your fingertips. And we can kind of see how this sort of would work, right? So again, like I say here, this expression is going to work fine for uniform electric fields, and we're going to see what happens if we have non-uniform electric fields in a moment. But for uniform electric fields, this is going to work fine, and we can kind of see how it works in these 3 diagrams below, right? So here we have our purple or pink or whatever electric field lines, and we can see them going through our surface. We have our area vector normal to the surface, so it's perpendicular, it's pointing, away from the surface. And so we can see that if we did that dot product, we would end up with some value for our electric flux. But if we now tilted our surface slightly, right? So we tilt our surface some angle phi, and then we're going to have a small offset in the pointing in the direction of our area vector versus our electric field vector, right? And so we're going to have somewhat less flux going through there. And in image C, we can see that our electric field lines and our area vector are directly perpendicular. And so the electric field line doesn't puncture through the surface at any point, so we have no flux going through the surface, and we can see that in this diagram. Now all this works fine because we have a uniform electric field, right? Like all these electric field lines are very uniformly spread out here, And so as our surface turns, we know exactly what to sort of do here. But let's say we did not have a uniform electric field, right? If we didn't have a uniform electric field, and the electric field was somewhat, say we take this for example, the electric field was somewhat stronger up here, and then it got weaker as we went to the left, and it got stronger as we went down or something, and it wasn't uniform, then we'd have to be more careful about how we did this calculation, right? We would have to very carefully break up our surface into a number of tiny little tiles, like we've done before with the electric field. Like when we're calculating the electric field outside of a charged rod, we break up the rod into tiny little areas, or when we did the disc or a surface, we break it up into tiny little tiles, and we consider the electric field protruding through that single tiny little infinitesimal chunk of tile, right? So if we do that and we sum up over the entire collection of tiles that make up our surface, we can again regain our expression for the electric flux through our surface, okay? And that's exactly what we see happening here, right? So what are we doing? We are taking the double integral over these tiny little infinitesimal areas, which will be dotted into our electric field at the point where that tile is, and we integrate over all of them. When we do that, we regain our electric flux, okay? And so these two equations, equation 4 and equation 5, are really the key ideas that we want to take away from sections 22.1 and 22.2. They're the ideas that we're really going to need to make use of when we're looking at Gauss's law. And before we get to Gauss's law, like I said, in the next video, I'm going to be doing a bunch of examples where we're calculating electric flux, both for a uniform and for a non-uniform electric field through different types of surfaces. We'll do some integrals. We'll take a look at it all, and it'll kind of bring all these ideas into focus. But from this video, you really want to take away equations 4 and 5 and this idea that our area is no longer something that we should think of just as a number. We want to be thinking of our area as a vector, which points normal to the surface and has magnitude equal to our scalar value a, how we normally think about area. Okay, so I'll see you guys in the next one for some examples.